Am I audible?
Yes, sir.
Okay.
Yes, sir.
So in last class we were on the momentum transfer problem, where we have to derive the equation to correlate the driving force, that is the pressure difference in a pipeline, to the flow rate. Okay, so how the flow rate will affect the how the driving force will can be correlated to the flow rate. Okay, that is the flux of the momentum flux. Okay, so for that we have first there are different steps of the derivation. So first you have to draw the diagram of the system. First step. Second step, put the accurate coordinate system at accurate space. So you have to put the in this problem you have to put the cylindrical coordinate system at the central of the pipeline. You have to remember the few points, that the coordinate system should be aligned with the geometry of the system. Okay, so if the geometry is cylindrical, then you have to consider the cylindrical coordinate system. If geometry is rectangular or the flat surface, you have the flat surface, you have to consider the Cartesian coordinate system. If you have the spherical geometry, system has the spherical geometry, then you have to consider the spherical coordinate system. Okay, so these are the important steps. Now, how to put the coordinate system? You have to consider, you have to put the coordinate system in such a way that the system will become the symmetric. Okay, the best way to put the coordinate system in this problem, you can put at the central of the pipeline. At the initial origin should be at the initial point. Okay, then the system will be symmetric. Okay, and if you put any other place the coordinate system, you can also solve the problem. Then also you can solve the problem, but problem is, but you have the mathematics which required, that will be more difficult, and you may not get the final answer, okay, easily. Then second point, you have to take the assumptions. So what are the main assumptions in this case? First thing, why you need the assumptions? Because mathematical modeling required some simplification. Okay, you cannot mimic the nature with the 100% accuracy. You need some simplification so that you will get some simple mathematical equation which can significantly mimic the problem. Okay, so first assumption which you have to take in this condition is the fluid density and viscosity is constant. What is the meaning of this assumption? Fluid density and viscosity are constant. That means there is a liquid. This is a liquid fluid, and the fluid which is flowing inside the pipeline, that is the liquid phase, is in liquid phase. That means density is constant. Second, viscosity is constant. That means it is a Newtonian fluid. Okay, because in the Newtonian fluid, viscosity is only the function of temperature. Here we are not considering the temperature difference. So temperature is constant, that's why the viscosity is constant. Density and viscosity is constant. Second assumption which we have taken here is the steady state. Steady state means all parameters are constant with time. This is a continuous process where the parameters are constant with time. Parameters are not changing with time. If you want to solve the problem for the unsteady state where the parameter depends upon the time, then problem becomes slightly more complicated. You can solve with the unsteady state also, but in most of the chemical engineering plants, you find the steady state condition only. Okay. Third condition, laminar flow, because in the turbulent flow, all parameter depends upon the time. And the micro level, you have the fluctuation in the flow at the local level, you have the fluctuation in the flow. Okay, so that is very difficult to solve then. So we assume the laminar flow. In this subject, we will only solve the problem related to the laminar flow. We will not go for the turbulent flow in this subject. For the turbulent flow, you have to use the computational fluid dynamics. You need the supercomputing powers to solve the turbulent flow problem. The equation will be same, the procedure will be same, only the mathematics will be more complicated, very complicated. You have to solve the higher order partial differential equations which require a lot of computational power. Okay, the next assumption, Newton's law of viscosity is applicable. That is true because you have the constant viscosity. You are solving for the simple fluids like water, oils. For that, Newton's law of viscosity is applicable. Next assumption, fully developed flow. So I have already taught you that what is the developing flow and fully developed flow. Initially, where the velocities are changing due to the presence of solid body, that is called the developing region. So we are solving the problem for fully developed region where the velocities are constant with length. Okay, so this condition is true when you have the L by D ratio. The L by D ratio is greater than 50. Length versus diameter ratio of pipeline is greater than 50. Then you can assume this point. And fully developed. So for most of the problem, this is true. And that means if L by D ratio means the length of the pipeline is greater than the 50 times greater than the diameter of the pipeline, that means the developing region can be neglected. The developing region where the velocity is changing with the length of the pipe, that can be neglected. And that is very small in comparison to the whole length. That can be neglected. Okay. The next assumption, that is no slip boundary condition. What is the no slip boundary condition? This tells you whenever the fluid, a flowing fluid comes to the contact with a solid body, then the velocity of the the velocity of the fluid at the interface is equivalent to the velocity of the solid body. Okay, so at the interface where you have the surface of solid liquid interface, the velocity of the liquid is equivalent to the velocity of the solid body. So in this case, the tube is in stationary condition, only fluid is flowing. Tube is not moving. Tube is in the pipelines are in the stationary condition. Only the fluid is moving inside the pipeline. So you can assume the velocity of the velocity at the r equal to r at the internal diameter of the tube wall and the fluid interface, that is equal to 0. Velocity at the in the interface is equal to 0, and from the no slip boundary condition. So these are the 6 assumptions which are required to solve this problem. After taking this assumption, now you can solve this problem very easily. Okay, now we will go for the next step. So this is the assumption is the third step. First step is
जाओ
yes.
शर्म नहीं आ रही जबरदस्ती बोल रहे हैं।
हाँ भाई।
दीदी आप भाग जाओ यहाँ से। दीदी
भाई
बिरयानी बना दो केवड़ा वाटर डाल के।
हाँ भाई, शिव शंकर जी आप अपना माइक म्यूट रखें। ठीक है, तो नेक्स्ट, तो फर्स्ट step is draw the diagram. Second step is put the coordinate system at accurate position. Third step is take the accurate assumptions. Now you have to go for the fourth step. Now the fourth step is select the accurate velocity, non-zero velocity component. Okay, selection of non-zero velocity component. Okay, that is very important in this problem. Okay, what is the meaning of the non-zero velocity component? Velocity is a vector quantity. It has the 3 components. So in this diagram, we have selected the cylindrical coordinate system. Okay, so velocity in this case, velocity v has the 3 components: v z, v r, and v theta. Now, in most generalized form, in the most generalized form, Vz may depend upon z r theta and time t. These are the dimensions. So Vz may depend means the velocity may change in the z direction also, in r direction also, in theta direction also, with time also. Similarly, Vr, the Vr component of the velocity, that may also depend upon z r theta and time. Similarly, d theta component of velocity, that may depend upon z r theta and time. 1 minute. Okay, so in any problem where you have the cylindrical system, so this is the pipeline, you have put the coordinate system like this. This is the z axis, this is the r axis, and this is the theta axis. Okay, now you are so here velocity, fluid is flowing in this direction right now. Okay, so here you, the velocity may have the vz, vr, or v theta component. That may depend upon z direction, r direction, theta direction, and time. Okay, now we have to cut down the quantities which are zero. Okay, now check this diagram. Okay, in the r direction, this is the r direction, this is a r direction. In the r direction you have a solid boundary. In the r direction you have a solid boundary. So when you have the solid boundary in the r direction, there is no way that fluid will flow in the r direction. Okay, if you have a solid boundary in one direction, the fluid cannot flow in that direction because there is a solid boundary, है ना? Fluid cannot permeate this until unless this pipeline is porous. Fluid cannot flow in this direction. So VR will be zero. VR will be zero because in R direction you can't have any velocity profile. So VR will be zero. Now comes to V theta. Okay, here pressure is P1, here pressure is P2. And you assume that you have the laminar flow. Okay, you have a laminar flow. Okay, so when you have a laminar flow means systematic flow. Okay, you have the pressure drop driving force in this direction, in the Z direction. Your driving force in the Z direction, and the flow is laminar, means simple shear systematic flow. So fluid is flowing very slowly, layer upon layer. Okay, there you have a layer upon layer systematic flow in the Z direction. So why the fluid will rotate in the pipeline until unless you have some specific geometry which will facilitate the rotation of the fluid, or you have the driving force in the theta direction. Fluid will not rotate inside the pipeline automatically. In the laminar flow region, if you have the turbulent flow region, there are chances there are eddies will form in the flow. Okay, in the turbulent flow region, there may be theta directional flow, but in the laminar flow region, because flow is very systematic, very slow and systematic, and driving force occurs in z direction only, d theta will be zero. Okay, that you have to select which components are zero, which components are not zero, based on the assumption and your intuition. Okay, your general knowledge of the system, and because there is a solid boundary, the fluid cannot flow in across the solid boundary, so VR will be zero. You are forcing the fluid in the z direction only, and flow is very systematic, very slow and very systematic, so there is no reason fluid will rotate. Okay, there is no reason fluid will rotate, so V theta will be zero. Okay, so these are the two quantities that will become zero. V theta will become zero, VR become zero. Now you have the Vz only. Okay, now Vz may depend upon Z, R, theta, and T. Okay, Vz may depend upon Z, R, theta, and T. So we have assumed the steady state. Steady state means all parameters are constant with time. All parameters are independent to time. So Pz will also not depend upon time due to the steady state condition. So Pz will not depend upon time. Okay. Now check the V theta direction. This is the pipeline. You have this V theta direction. Now the system is symmetric, that's why we have taken the central as a the coordinate system. We have put the coordinate system in the central point. Okay, so if you check the distance, r distance from the theta in any theta direction, the velocity should be equal because system has a symmetry in the r direction. That the distance from the solid boundary is equal from the z axis in all theta direction. Suppose you have the theta equal to 0, theta equal to 30 degree, theta equal to 90 degree, or theta equal to 120 degree, 180 degree, or 270 degree, or 360 degree. So in all 360 angles, when you move for a constant r the distance, you have the same velocity. Okay, that means Vz will not depend upon theta. ये समझ में आया? Why the Vz will not depend upon theta? Because you have the symmetry in the theta direction. Okay, the distance of solid boundary in all theta direction is same. That in all direction you have the r radius, because that is the central of the pipeline. Okay, so you have the symmetry in the theta direction. So Vz will not depend upon theta. Okay, so Vz theta equal to 0. Vz will not depend upon theta. Now you have the Vz which may depend upon either the z axis or in the r axis. You have the Vz which may depend upon either the z axis or in the r axis. Okay, so fourth point is selection of non-zero velocity components. So we have selected the non-zero velocity component, that is Vz, which may depend upon z or and r. Okay. Now we can use the fifth point is use the equation of continuity. Use the equation of continuity. Okay, so what is the equation of continuity for this? Is the incompressible system, density is 0. So the equation of continuity for incompressible system is del dot v equal to 0. Del dot v equal to 0. That is the equation of continuity in the vector form. Now you have to write the equation of continuity for the cylindrical coordinate system. So I have already written here equation of continuity in the cylindrical coordinate system. This is the equation of continuity in the cylindrical coordinate system. Okay, so first we will write this equation in the cylindrical coordinate system. Okay, so this will be given to you in the exam, and you need not to remember this. Okay, that will be discarded. Okay, so you will get the non-zero velocity component, that is Vz, that may depend upon z and r. This will 0, this is 0, this is 0, this is 0. Okay, now you have to use the equation of continuity. That is del dot v equal to 0. Okay, now you have to write for the cylindrical coordinate system. So for cylindrical coordinate system, del rho by del t plus 1 by r del by del r rho r vr plus 1 by r del by del r del by del theta rho v theta plus del by del z rho vz equal to 0. This is the equation of continuity in this form. Not in this form, that is basically you have del rho by del t plus del dot rho v equal to 0. So the extension of this equation in the cylindrical coordinate system is this. Okay, now we have assumed the density is constant. So this is 0 because density is constant. Here you have the VR. VR is 0. In the fourth step, we have already showed you that the VR is 0 because there is no reason fluid will flow in the R direction. You have a boundary in the R direction. So VR will be 0. V theta will be 0 because you have the symmetric geometry in the theta direction. In all theta direction, you have the same velocity. You have the symmetry in the theta direction. So V theta will be 0. There is no reason fluid will rotate. V theta means fluid is rotating inside the pipeline. So because fluid is flowing with very slow speed and very systematic way, so the fluid cannot be rotated. So V theta will be 0. So the first three steps, the first three part of the components of the equation are 0. So you will end up with rho del rho Vz by del Z equal to 0. Okay, now take the rho out because rho is constant. So you will end up with rho multiplied by del Vz by del Z equal to 0. Okay, now in this equation, density cannot be 0. Density is a physical quantity. For any physical fluid, density is a positive. Density should be a positive number. It cannot be 0. है ना? So you will end up with del Vz by del Z equal to 0. That means Vz is constant in Z direction. Okay, so when you use the equation of continuity, it tells you that Vz cannot depend upon Z direction. Okay, now you will get, initially we assume that Vz may depend upon Z and R direction. Now from equation of continuity, you can say Vz cannot depend upon R direction from equation of continuity. Okay, so you will end up with, so non-zero velocity profile, velocity component is therefore non-zero velocity component is Vz that may depend upon R only. Okay, you have the Vz that may depend upon R only. Okay, now this is the step fifth. Okay, now in the next step sixth, you have to consider the non-zero shear stress component, and you have to identify non-zero shear stress component. Okay, so you have the velocity Vz R. Okay, so this is the non-zero velocity component. So we will make the non-zero shear stress component from this only. So tau is the shear stress. Shear stress is the second order tensor quantity. It has the 9 component. In the cylindrical coordinate system, you may have the tau r, tau r theta, tau rz, tau theta r, tau theta theta, tau theta z, tau z r, tau z theta, tau z z. Okay, these are the 9 components of the shear stress. Okay. Now you have to remember the two things. First indices in the shear stress represent the, what is represented by the first indices, that will represent the direction of surface. Okay, when you write in form of, the in form of the force, है ना? In this case you have to just remember first indices represent the direction where velocity is changing. First indices represent the direction where velocity is changing. Okay, so here velocity is changing in the r direction. Okay, second point you have to remember, the second indices represent the direction of velocity. Okay, so that is the z direction. Okay, so first indices represent the direction where the velocity is changing, second indices represent the direction where the fluid is flowing, or the direction of velocity, that is the z direction. So this is only the non-zero velocity profile, tau rz, because r is the direction where velocity is changing and z is the direction where fluid is flowing, where the direction of the velocity is z. So tau rz is only non-zero shear stress component in this case, all others are zero or negligible. So you may have the condition, may have the problem where all other components are also not zero. Then the problem will become the more complicated. Okay, here we are solving the problem in the easiest way. Okay, so here you have the tau rz as a non-zero velocity profile. Okay, so we have completed the so tau rz. Here I am rewriting again. Therefore, tau rz is only non-zero shear stress component. Other side are zero. Okay. Now you have done this much. Now you have to draw the control volume. So next step, one very important step is, this is the step number 7. Draw the control volume. That is the next step. So there are rules in the drawing the how to take the, how to consider the control volume. So there are some rules. Okay, so you are solving the problem for the flow inside the pipeline. Here we are solving the problem for flow inside the pipeline. Okay, we have selected the middle central point of the pipeline as a central line as a z-axis. Okay, this is the r-axis and this is the theta axis. Okay, now how to, why you require the control volume? Because you have to do the momentum balance. You have to write the balance of the momentum or the force balance. The force balance can be only be occurred on a volume, and then you collect that volume to a point or to a line, then we will get the final expression. So how we draw the control volume? The first thing you have to remember, first thing you have to check, Which direction will fluid is flowing? Fluid is flowing in the VZ direction, Z direction, and it may depends upon the R. And in R direction, velocity is changing. That means the velocity depends upon R means in R direction, velocity is changing. At the end of the pipeline, velocity at the wall, velocity is zero, VZ is zero. At the central point, velocity will be maximum. VZ is maximum. So here, suppose the velocity is 2 meter per second. Here the velocity is zero. So the velocity is not constant throughout the pipeline. It is changing from this point to this point. Okay, so velocity is changing in the R direction. So now how to draw the control volume? So control volume should be generally control volume should have the same geometry as the system. Okay, then it is easy to do the balance. Okay, if you have the same geometry as the system, then you can easily do the balance. Okay, so geometry is circular, cylindrical here. This is the cylindrical pipeline. So you have to select the cylindrical cylindrical control volume only. Okay, so this is the cylindrical pipeline. Okay, so what we will do, we take a imaginary surface of distance r. This is the one end of the control volume. Okay, so that will be same. The control volume geometry should be same as the geometry of the system inside the. So basically control volume is inside the system. Okay, so whatever the geometry of the system is, the control volume geometry should be same. Okay, so we are taking the radius of the actual system, actual pipeline is capital R. So from distance R, we are taking a another surface, imaginary cylinder. Okay. Now the differential thickness of the control volume should be in the direction where the velocity is changing. The differential thickness of the control volume should be in the direction where velocity is changing. Okay, so this is inside the system. You have a control volume. Okay, so there are rules for control volume. First, the geometry of control volume should be same as geometry of the system of the system. So in this case, it is a cylindrical geometry of the length. The length of the cylinder is L. In this case, cylindrical geometry with length Now the second point is, second rule is the differential thickness of the control volume should be in the direction where velocity is changing. So in this case, this is in the R direction. In R direction, you have to take the differential thickness. Okay, so basically the control volume is, this is the central line of the pipe. So inside the system, inside the pipeline, you have make a strip. This is a strip inside the pipeline. Okay. Here, the inner radii of the strip is R, small r. The outer radii of a strip is R plus dr. Okay, so basically you, am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Okay.
Yes, sir.
So basically you have to take the control volume inside the system. Okay. The outside diameter is R. Basically, why you require the control volume? So that you can write the, this is capital R. This is the control volume. है ना? The main system is this, the pipeline. Inside the pipeline, you have the control volume. So why you require the control volume? Because you have to you have to write the momentum balance for this control volume. Then we will collapse the control volume to a line. Then you will get some differential equation which is true for the whole system. You will integrate the differential equation, you can determine the value of the velocity, value of the pressure at any point, because that differential equation will be true for the whole system, है ना? So this is the control volume. Now we will write the momentum balance for this control volume. Okay, you can understand the rule. The differential thickness dr should be in the direction where velocity is changing. Velocity is changing in the r direction. So dr should be in the r direction, and the geometry of the control volume should be similar to the geometry of the system, so that you can easily you can easily do the uh, whenever you write the equation, you can easily do the momentum balance. Okay, now we will write the momentum balance equation. So next step is momentum balance equation. The next step, this is the step 8, that is writing the momentum balance. Okay, so now how to write the momentum balance? First, what is the momentum balance equation? That is the second axiom of transport phenomena, that is rate of accumulation of momentum in control volume of momentum in control volume that should be equal to rate of inflow of convective momentum minus rate of outflow of convective momentum plus summation of all forces. Okay, so you have to write this expression for our system. So control volume, you have known what is the control volume. This is the strip, cylindrical strip inside the pipeline. That is your control volume. You have to write the balance, force balance for this equation. So first step, rate of accumulation of momentum in control volume. Rate of accumulation of momentum in control volume. So the rate of accumulation of momentum in control volume, that is equal to 0. Why? Because steady state. So there is nothing changing with time. Whenever you have the accumulation or loss, then the quantity will change with time. You have d by dt. You know, whenever you have the accumulation of mass, you have the dm by dt. If you have accumulation of momentum, you have the momentum, d momentum divided by dt. So that will be 0. Why? Because steady state condition. That is the first point. Now rate of inflow of convective momentum in the control volume by convection. So momentum flux entering in control volume by convection, that is equal to rho Vz square, then multiply by surface area. Okay, so rho Vz square multiply by surface area. Now momentum will enter from which part? So because fluid is entering in the control volume from this side, fluid is flowing from this direction, so fluid is entering from this surface in the control volume. We are doing the balance for the control volume only, not for the whole pipeline. So fluid is entering from this pipe, this space. So what is the surface area of this space? The internal radius is r, outer radius is r plus dr. So the you can calculate. I am calculating here, surface cross sectional area of the control volume. Area of the control volume. That is this minus this. Okay, so this area we have to calculate this area. Internal radius is small r, outer radius is r plus dr. So that is equal to pi r square, pi r plus dr square minus pi r square. Okay, that is the cross sectional area of the control volume. So when you expand this, you will get pi r square plus 2 pi r dr plus pi dr square minus pi r square. So pi r square and pi r square will be cancelled out. You will get 2 pi r dr plus pi dr square. Okay, now dr is very small. Therefore, dr square will be even smaller. Will be negligible. So you can neglect this quantity. You will get area, cross sectional area 2 pi r dr. Okay. So this is the cross sectional area. So here you have to write the cross sectional area, multiply rho bz square. Bz is the velocity, rho is the density. You have to multiply rho bz square, multiply by the cross sectional area. That is the 2 pi r dr. That is the amount of momentum entering by the convective momentum entering in the control volume from z equal to 0. Okay, that is the amount of convective momentum entering in the control volume. Now you have to write amount of convective momentum leaving from the control volume, momentum flux leaving from the control volume by convection, from the control volume. Control volume is also called the CV, by convection. That is equal to rho, same quantity, rho bz square 2 pi r dr. The liquid, the fluid will leave from the z equal to L. That same quantity from the z equal to L, that is leaving from the control volume. The fluid is leaving from the control volume from here, so that will take some convective momentum with it. Okay, so the amount of the amount of convective momentum leaving from the control volume is 2 pi r dr multiplied by rho bz square at z equal to L. This is z equal to 0 and this is z equal to L. Okay, so this is the amount of convective forces applied on the system. Now you have done the momentum, you have written the momentum. Now you have to add the forces. So summation of forces. So first is the pressure force. So pressure is a compressive force, है ना? It will work always in the inward direction, है ना? It will always work in the inward direction. So and there is a pressure difference in the z direction only. Here you have the pressure P naught. Here you have the pressure PL. So you have the pressure difference in the z direction only. So pressure will apply on the z direction only. In the other direction, you have the same pressure. On the z direction only, you have the different pressure. So at this surface, pressure will apply in this direction, P naught, and at this surface, pressure will apply in the this direction. So pressure multiplied by surface area, that is the amount of force applied on the system. Okay, so you have a pressure applied on the z equal to 0. Pressure force, you can write pressure force at z equal to 0 is P naught. At z equal to 0, you have pressure P naught 2 pi r dr. At z equal to 0, at z equal to L, you have the pressure force. At z equal to L is PL multiplied by 2 pi r dr cross sectional area at z equal to L. These are the two pressure forces. Okay, and this is in the negative direction. PL is in the negative direction, P naught is in the positive direction. Okay, so basically you have to check the this outer force. So in outer direction, if you check, this is the positive direction of z. If you check from the outer surface, it is the negative direction of the z. This is the direction of the force, pressure force. And at z equal to L, the pressure will applied in the negative z direction. At z equal to 0, pressure is applied on the positive z direction. Okay, so you have to check these two surfaces outside. Okay, so it will be the inward force. It will always apply in the inward direction, and it is a compressive force which compresses the system. Okay, so you have at this point, you have the force direction this, which is the negative z direction. At this point, the force direction is this, which is the positive force direction. Okay, now you have to write the second type of force which is applied in the system is shear force due to the friction. So second type of force applied in the system is shear force. So we have already know that only non-zero shear stress profile is tau rz in this system. Only non-zero shear stress component is tau rz. Now at which surface it is applied? Friction, because fluid is flowing in this direction. So friction is applied in this surface, at this surface, and at this surface. Okay, at the top and at the bottom, at these surfaces, friction is applied on the system. Okay, आप लोगों की क्लास तो नहीं है अभी? Have you class at from 2 p.m.?
Yes, so we have lab class.
Lab class. Okay, so we will continue in the tomorrow class. Okay. Tomorrow you have one class, then in that class we will continue this and we will complete this.
Okay, sir.
Basically I am going very slowly in this derivation, because after completing this derivation you should able to solve any geometry, and if I am giving you the triangular geometry, if I am giving you the flow outside the flow in the free flow of the fluid in the space, then also you have to derive similar type of equation. You have to follow the same procedure, है ना? And you can solve the problem. This is the simplest problem in the flow in the tube, but if you know the process, you can solve any problem, है ना? In this subject you should be able to solve every type of problem. At least you have to derive the equations, है ना? By reading the problems. Okay, so that is the requirement. That's why I am going very slowly at this point. Okay, so tomorrow class we will complete this problem.
Okay, sir.
Thank you.